Hello everyone, this is Preetham Prathipati, and today we are going to discuss about my final project, which is a case study on recognition of emotion from images. Let us go through this project. So we have introduction, problem statement, model features, technical summary, dataset, code demonstration, output, results, advantages, limitations, and conclusion. So basically, in this project, we aim to solve the problem of real-time emotion recognition from facial images. We take facial images and we recognize emotion from those images in real time. Either let it be real time or from normal images, we tend to recognize emotions from the facial images. And we have classifications such as happiness, sadness, anger, surprise, fear, disgust, and neutral emotions. These are the ones which are we hoping to identify in real time. And also we are employing a convolution neural network for classifying emotions in these images. And these convolution networks are particularly effective for image-based tasks due to the feature extraction of capabilities. And their architecture includes convolution pools, layers, fully connected layers, and it is also trained to predict the probability distribution of images for emotions for each input of image. Our system can be deployed in video conferencing applications. It can be used in educational platforms, customers like we can also use it to gauge customer satisfaction during live interactions, which we can use to process you know uh, which we can use to improve sales and services. And this real-time processing ensures very minimum delay, enabling seamless integration with our live video feeds. So our problem statement has one single, like two problems. See, we always want to know about like how good it's performing and how less time it's taking to performance. So time and performance are really good constraints, in any problem. So we also have the same constraints, which are like we need our model to be fast and executing really fast. For example, uh, we want to identify an image. It needs to be implemented fast, and also our performance should be great. We need to get a great accuracy. So we are developing a system which we which will accurately classify emotions with minimal time. This is our problem statement. We aim to develop this. And our challenges have like high classification accuracy and really swift processing speeds. And we tend to enhance applications in human computer interaction and mental health monitoring, intelligent tutoring, and many other platforms. So our model features contain deep CNN architecture, which has multiple convolutional and pooling layers with increasing complexity for each effective feature extraction. And we use regularization techniques, which are batch normalization and dropout, to enhance training efficiency and prevent overfitting. Our data augmentation it enhances our dataset variability, and it has really good robustness against real world variations. Like our dataset may not be really good with our real world dataset, so we use data augmentation to deal with it. And real time processing is used to have low latency interference and enabling seamless integration with live video streams. So we can also use this on live video streams. And we have comprehensive emotion classification, which we have 7 distinct human emotions, which facilitate diverse application of use cases. And we also have an efficient deployment using OpenCV for face detection and real-time visualization, which is very real user-friendly and which has immediate feedback. And our technical summary consists of a layer composition, which has multiple convolution layers with increasing filter sizes of 32, 64, 128, 256, each followed by batch normalization and max pooling layers to effectively extract and reduce spatial features. Our regularization contains dropout layers, which are incorporated to prevent any kind of overfitting by randomly deactivating neurons during training. And we do normalization, which we resize the images to have 64 by 64 pixels, and they are normalized to a 0 to 1 scale to standardize. It's called standard normalization. And we have augmentation techniques, which we discussed before, such as shear transformation, zooming, horizontal flipping, using our image data generator to enhance model robustness and generalization across spatial data. We have compilation parameters such as Adam optimizer, sparse categorical cross entropy as a loss function, and accuracy as our evaluation metric. Our loss function and accuracy are evaluation metrics. And we train the model on the FAIR 2013 dataset, which is Facial Emotion Recognition 2013 dataset for 50 epochs, leveraging both training and validation data generators to monitor performance and prevent overfitting. And we use OpenCV's HAR Cascade classifier to detect face in live video streams using a webcam. So we pre-process the live feed, pre-process the facial data, and we apply our neural network on that. We predict if the person is angry, disgusted, fear, happy, neutral, sad, or surprised for each detected face by outputting probability distributions. So our user interface does a bounding box for recognized faces using HAR Cascade's frontal face algorithm, and which after we detect the facial expressions, then we apply the algorithm, then we detect emotions. And we have a really good efficiency of 24 milliseconds to 36 milliseconds per image, which is a really good accuracy, really less time. And we have applications for this which are designed to have into various platforms such as video conferencing, educational tools, mental health monitoring, and customer service systems. So this is our data set. Our system leverages like a facial emotion recognition 2013 dataset, which has 28,709 training images, 7,178 validation images across 7 emotion classes, which are anger, disgust, fear, happiness, neutral, sadness, and surprise. We are pre-processing it for 64 into 64 pixels, and we are normalizing it into a standard scale of 0 to 1 for our CNN. And we use Keras image data generator to implement shear, zoom, horizontal rippling as data augmentation methods. This is our code, which I will demonstrate in a while. So basically, this is our emotion prediction training, which we had as this FAIR data set. We import the data set here. Then we have train and testing part. We see where the train is getting stored and testing gets stored. Then we have our CNN here, which has max fluidity, batch normalization, dropout layers, every layers here. Then we have dense layers, batch normalization, dropout, and we compile here using ADAM optimizer and sparse control entropy, cross entropy loss with our metrics as accuracy. And this is the image data generator, which we use to have augmentation. Then we all do this and we run 50 epochs, which will take a quite while if you don't have a GPU. And at the end, we can observe our training accuracy is 69.77, which is almost equal to 70. Our loss is very low, which is 83. Our validation accuracy is 62%, which is a good validation accuracy. And see, this is one of the training data set, and which we open and we check if the recognized emotion is correct, and it is showing correct. And now we save our model, and we save our model, save our weights, and we wait for it. And we move on to the next code. In our next code, we load our saved model, and we define the emotion labels, and we have the HAR Cascade frontal face default algorithm, which we use for face detection. So in this whole process, what we do is we first detect the face, draw a bounding box on the face, and put an emotional label after detecting it. So we predict it, then we label it. This is how it works, and this shows how much how fast it is predicting. Since it's already pre-trained, it's detecting pretty fast, which is equal to 20 milliseconds. So as I'm using the webcam right now, I cannot show you the real webcam, but what I can do is I can show you the images which I took before this and implemented it. I'll show you just a second. So these are the three images which I took. You can see the differences between images. So out of these three images, it detected this as neutral, this as angry, and this as happy, which is pretty accurate. And we use this to provide a classification report and also a confusion matrix. And we also have a per class accuracy in which we can say happiness is like really good, which we will discuss in this PowerPoint again. So as we can see, this is our output. We detected neutral, angry, and happy, which three of our images, which is detecting pretty well. And our results contain confusion matrix, in which we can see the happiness label is getting really good, which has really good ratio of true to false positive ratios. And our classification report consists like our results per class versus accuracy, in which we can see disgust is getting really low accuracy, but our happiness, neutral, sadness, surprise, fear, and angry, everything is like almost getting a very good accuracy, which we can use to accurately generate. And these are our results. Like our results contain like a really low latency for fast and efficient emotion recognition, and it has anger, disgust, fear, neutral, sad, surprise, and with notable successes in different emotions. We use these emotions using efficient convolution layers, normalization, data augmentation, which will result in robust predictions for diverse facial expressions. We used hard cascade frontal face algorithm for different type of feature recognition. We detect face first, then apply emotion recognition onto it. And we validate for its potential for live emotion-aware applications in mental health, customer service, and video conferencing, while also addressing challenges such as facial occlusions and variability. So our advantages are we can use this for mental health assessments in educational platforms, in video conferencing, which can pretty much help us define how empathetic and effective communication is in all this. And in customer service sector, we can always gauge how much satisfied the customer is during live interactions, so we can respond promptly and improve service quality based on real-time emotional feedback. And we have several limitations which are like occlusions. Occlusions is nothing but face marks or anything which partially covering the face, like my specs. So, which will affect the model's ability to accurately detect the emotions. So, our critical face features are needed for the model to detect emotions clearly, which is being hindered by these occlusions. And we also have this poor lighting conditions. As you can see, I have very poor lighting conditions, which will make it really difficult for conventional network to extract reliable features. And like right, our expressions are not just are not just restricted to seven emotions. We have way more than that. So if we have way more than that, it's very difficult to like generalize and accurately classify a wide range of emotions. That's one of the limitations. So, in conclusion, we can say that our real-time emotion prediction using CNN successfully demonstrates the feasibility of real-time emotion recognition from facial images. We leverage a convolutional neural network and we achieve a prediction speed of 24 to 36 milliseconds per image. And we accurately classify seven key emotions. So we include efficient pre-processing techniques, image resizing, normalization, and data augmentation strategies that enhance generalization across facial expressions. The use of lightweight CNN architecture ensures fast processing times, making it suitable for real-time diverse lighting conditions. And also the system maintains its reliability by incorporating robust training data and augmentation techniques. This highlights the importance of data preprocessing, model optimization, and real-time performance for live applications. Our future work may involve expanding the dataset to cover more facial variations. As we said, like our face is not just limited to the seven emotions, we may have more emotions, and we can expand the dataset for more emotions, and we can improve the model's robustness against occlusions, exploring multi-sensory integration like audiovisual input. So we are only getting visual input here. So if we can also get auditory input, which will, I believe it can really enhance emotion recognition. So this is the summary of how our data went, how our project went. And I want to show you the link of this data set which I took from this. Angry has 958 files, Disgust has 111 files, which is the reason for its low accuracy. See, you can see it has pretty low files, and out of all these, Happiness has 1774 files, which is the highest, which can be a reason for it. So can be a reason for our low and high accuracy among our confusion matrix. And that will be all for today. And I hope you like this presentation. References and all the other things will be mentioned in the content. Thank you so much for listening until now. Thank you.